So what the exam boards say we need to know about is, as it says here, we need to talk about the things like the effective storage space required, number of comparisons, exchanges, etc. when you are running sorting algorithms. Now, these factors here all affect how long it's going to take the sorting algorithm to complete. So, and also how efficient the program is. And then down here, we've got these two other parts of the specification, which say that we need to use this thing, big O notation, to talk about the efficiency. And specifically, they refer to sorting and searching algorithms. Now, you can do this big O notation with anything. So we're going to kind of look at it really as a kind of general tool. And then we'll come back to sorting and searching specifically later. But as it says here, it's all about, you can see if I can get a pen. Look at this. It's all about the efficiency of algorithms. So how can we formally specify this algorithm is more efficient than that one? And what we've got to do first of all is look at things kind of mathematically, and then we'll look at it from a computer science point of view, because it probably makes more sense to do that. There is a mathematical proof you can do for big O, but that's really well beyond the scope of what we're going to be talking about. So if you remember from your maths, if you have a linear function, so this is one in which this is the kind of the equation that we'd use for a linear function. It's ax plus c, or if you think of it in the equation of a straight line on a graph, y equals mx plus c. If we plug in some numbers into this, if we I've just set the constant a as 4, and in this case c is 12, and then if you plug in some numbers like 1, 10,000, 1,000, and 10,000, we can see how the function grows. So on the right hand side here, we've got the result of our function for various inputs on the various x values on the left. And what we can see is, if you look at this equation here, and I'm particularly interested in this term here, the 12, which is the c, is that as the amount of input, as the size of the input grows, as the size of x grows, we get to a point where the value of c, which is 12, becomes very insignificant when compared to the result of the function. So if you look at it, obviously 12 is quite similar in size to 16, but 12 is insignificant when you compare it to 40,000, so down the bottom here. So that means that if we have an algorithm that behaves a bit like that, what we can say is the size of this last term here is completely and utterly irrelevant, and we'll see how that fits in with later on. Excuse me. So this here is, if you plotted out a linear function, you'll get a horizontal line like that. And if we look at this in terms of a computer program, then regardless of the size of the input, the runtime is going to be constant, and we'll see an example of that later on. You then get these polynomial functions. So a polynomial has an equation like this. So ax to the n plus bx plus c. And if we plug in some values again, one of the easiest ways of seeing how this works is just simply set the constants to some values, and then just calculate the value of the function for various values of x. So we can see with 1, we get an output of 22. With 10, we get an output of 472. With 10,000, we get an output of it's 400 million. So what we can see is as x increases, the only real significant value here in this function is this one here, which is x squared, this first term. So as the value of x goes up, the value of 6x and the value of 12 start to become completely insignificant compared to the actual overall value of the function. So therefore, x squared is the important term. And if you plot one of those on a graph, you'll see it grow like this. So you get this kind of beautiful little curve that just heads up, and the line becomes very, very close to vertical very quickly. If we get an exponential function, these are quite pertinent at the moment, obviously with the current health epidemic. They're in the form a to the power x, where a is a constant. So if we just take the value 2 here and plug in some values of x, what we find is 1 produces a result of 2, 10 produces a result of 1024, and 100 produces a result of a number to the power 30. So as you can see, this last term here is absolutely gigantic. So what we can say is the function becomes very big and it happens extremely quickly, and you get this kind of curve. It has a different characteristics to the polynomial, but it's kind of similar kind of thing, but it grows a lot faster. And if you look at COVID and the way the viruses spread, which is why this is so pertinent at the moment, you've got exponential growth, and this is an output from a computer model. And what this guy's done is they've plotted out the predicted increase with no distancing, because that's the way viruses propagate through a population. And then over on the right, the black and the blue lines are the effect of introducing social distancing, because that cuts down the transmission. And as you can see on the right hand side at the top here, I can't point at this on this level here, we have this blue line, and that shows that if they introduce distancing, then the virus starts to decay, and you get exponential decay of the growth of the virus, which is the blue line. But if you introduce the measure 1 day earlier, then you get the black line, and this was the predicted number of cases in the USA. And you can see if they introduce social distancing 1 day earlier, it has a huge effect. Now, and this is the problem with it, it grows very, very quickly. These exponential systems grow and shrink very quickly, relatively speaking. Now, if you've got a logarithmic function, we have this equation here. So the function is of the form a log of x, where a and n are the constants. What we can see is, again, if we plug in the numbers and then calculate some results, with a value of 1, we get an output of 0. With a value of 8, we get an output of 3, and with an output of with an input of 2 to the power 20, which is a very big number, million. Every million we get an output of 20. So what this tells us is we get a kind of we get very slow growth. And then we'll look at factorials. So factorial is a method of looking at permutations. So 3 factors here, or three values, A, B, C. What are the number of permutations? We can arrange those in. The answer is 6, which is 3 factorial, so 3 times 2 times 1. And with these, we get very rapid growth. As you can see here, the factorial line is the, excuse me, the purple line on this graph. The orange line is the exponential line. And then, well, you might think, well, how's that all relevant to what we're doing? And the answer is it relates to this thing. Well, it relates to this thing called time complexity. So time complexity talks about, as it says, how long it takes for an algorithm to complete with different data volumes. So if you've got a number of terms that you're feeding into an algorithm, like 5 or 500 or 5 million, how does this kind of piece of code perform differently? The problem is that if I write a program and we run it on, say, this laptop, and then we run it on a desktop computer, and then we put the same algorithm onto a supercomputer, the completion times will change. And in addition to that, if I run the program now and I run it in, say, half an hour's time, when I'm running many more programs on my computer, or fewer programs, or maybe when the machine's doing a backup or something like that, the performance is going to vary. So what we want to do is we want an approximation, a method of approximating how this thing behaves, and then how it's going to change its behavior in terms of changing the amount of data we're feeding in. So we've got 2 kind of principal challenges when you're writing software. The first one is this one here, which is what we normally think of as performance, which is getting the algorithm to complete very, very quickly. And then the second one is this one here, which is getting the algorithms complete using fewer resources, like less memory. But both of these presuppose that your algorithm first does what you want it to do. So the first challenge, for example, if you're writing a sort algorithm, is that you write an algorithm that does a sort. And then the next challenge is trying to make it either complete rapidly, or complete using little memory, or complete using rapidly using little memory, which is really quite challenging. And we specify these, so you can talk about algorithmic efficiency using big O notation. So the first kind of form of big O notation is this one, O to the 1, or an O of a bit. We'd talk about a big O of 1. And what this means is that the program takes the same amount of time regardless of the amount of input. So if we've got an array here, like this one here, this array is called list names. It doesn't matter how many items we've got in this array. If we want the size of it, it always completes in exactly the same amount of time. So we can have an array with 2 elements in it, or array with 2,000 elements in it, or 2 million elements. If you ask for the length of it, it will take the same number, the same amount of time to complete. So therefore we say this algorithm, or this function here, has constant time. It doesn't vary the amount of time it takes. And then we've got linear time. Excuse me. And what that means is that the time the algorithm takes to complete is directly dependent upon the number of data items. And a good example here is a linear search. So if we did the thing of taking a phone book, for example, and looking for a value, a person's name in it by looking at page 1, then page 2, then page 3, then page 4. As we increase the number of items we've got to search through in our list, the execution time increases. So as it says here, you can see this 10 items, you're going to take on average 5 to find what you want. If we take 1 million items, it's going to take on average 500,000 comparisons to find the value that we want. And you're going to get this linear growth, like a linear function. And we express that by saying, oh, it has a big O of n. Now, if we're looking for a polynomial function here, we say this has a big O of n squared. This is the time to complete, and it's as it says here, time to complete is a in direct proportion to the square of the number of data items. And an example of that is any algorithm that uses 2 nested loops. So a lot of sort routines use 2 nested loops, one loop within another. And if you've got an algorithm like that, the completion time is going to be proportional to the square of the amount of data. Because what happens is this kind of thing. If we think about like a bubble sort, in a bubble sort, this is the sort where you have an item. Let's say we'll have an item A. We're going to have a list here, and we will put some items in it. And this one's going to be a Z, and then we'll have an H, and then we'll have a P, and then we'll have an O. And in fact, let's get rid of that A from the start of the list and put it at the end. And what's going to happen, of course, is the way the algorithm works is it compares the first 2 items in the list, compares these 2, and it will then, they're in the right order, so it wouldn't bother swapping those. But then the algorithm will look at D and Z, and it will say, okay, they're also in order. So now we'll look at Z and H, and what it will have to do there is swap those 2 around. And we do this pairwise comparison working through the list. And if we have to swap anything, so in this situation, we've swapped these 2 in the middle here. What would happen is we know that it's unlikely the data's sorted. So we're going to go back to the beginning and start searching through the list again, swapping stuff in and out as appropriate. So you've got a loop within a loop. Now, one way you can code this is that you have a flag which says that you swap stuff. You iterate through the data, and when you get to the end of the list, you say, okay, if I have swapped something, I need to go through the list again because there's a chance that the data is still not in order. You might remember that with a bubble sort, you have to iterate through the list at least one more time. If you're doing swaps, you will have to iterate through the list once more just to confirm that the data is in order. That extra iteration is not really significant when you compare it to the number of swaps you're probably going to have to do. So if we take the worst case scenario and the kind of list is in reverse order, it's going to take an awful lot of iterations to get to the point where the data is in order. And you'll see that the increase in processor time is polynomial. Now, with look, when you're looking at sort algorithms, one thing that the execution time heavily depends on is how unsorted the data is before you start the algorithm. And with some algorithms, if you have sorted data, they're incredibly efficient. If it's kind of reverse order, then they're incredibly, you get algorithms that are very good at dealing with that. You get algorithms that are terrible at dealing with data in reverse order. So you can improve these things quite significantly. And as it says here, if you change the terminating condition of the for loop to reduce the maximum count every time you work through the data in a bubble sort, it becomes more efficient. So this is where what happens, if you imagine this Z here, as that kind of bubbles its way up to the top, when we get to the very end, what we now need, when we're iterating through the list now, we no longer need to look at that Z because we know it's in the right place. So we can actually just iterate through the items at the start of the list, and it becomes more efficient. So the we say it's a polynomial, or this has a big O of n squared, but the truth of the matter is that we can't ever calculate the time for completion and say it's absolutely this unless it's a constant time situation. So anyway, you would then get this thing called exponential time. We say this is a big O of 2 to the n, and or exponential time. And an example here would be producing a Fibonacci sequence using recursion, and we often see this. Every time we add one extra data item, the time taken to complete the job doubles, and that means that it's not the most efficient way of producing the result, or it's not the most time efficient way of producing results. Anyway, if we then have a logarithmic time here, here we express this as saying it has a big O of log n. Time increases very slowly as you increase the number of data items. So the classic example here is the binary search. So if you remember, if we have a graph like this, and at the bottom I've got my I've got the number of items. Oops, and then at the time here I've got the time in seconds. What's going to happen is if we've got linear search, we're going to get a line which is quite steep like this, and we say this has a big O of n. Must apologise for my handwriting. I'm going to draw this using a mouse, and it's quite difficult. Now, if you have a binary search, what's happening, of course, is you've got this list, and you're looking at the item in the middle, and then you're saying, okay, the target is, let's say the target's over here. What we're going to do is we're going to discard this half of the list here. So we've now got half the amount of data to look at. And we're going to keep on doing this. If you remember, we call this a divide and conquer algorithm, because we take that every time we look at the data, we divide it in two. So what happens every time you look at the data, you've got half the amount to look at. And the growth of this algorithm will look a bit like this. So we say that this has a big O of, I can't really write this at the side. This is our logarithm, and I've run out of space here. But this is the algorithm. This has a growth factor of log n, and what's happening is this line is becoming very, very, very flat as we increase the number of data items. Now we can look at the increase in time. If you imagine we've got, say, this many items here, and then we double the number of items here. The difference in time for these two items, in the case of the linear search, this straight line is going to be twice as great. But in the case of our binary search, it's going to be the difference between this amount here and this amount here, and we get a very small increase. And when the number of items becomes very, very significant, the growth in time becomes fairly insignificant. And this is one of the reasons why binary searches are so efficient. And generally speaking, if you've got an algorithm which does divide and conquer, you're quite likely to get logarithmic growth in terms of time. Now we also get exponential growth, and this is where the time to complete grows very, very fast, and it grows much faster than the kind of other O of 2 to the n. So password crackers using brute force are a good example of this. So if we take a password cracker, I've given some arbitrary rules here, which we've said the password's going to use lowercase characters. If we have a if you use the, and we get in, I've given this rule here, which is basically that we can only have use each letter once, which is unlikely, but it's possible. So what we're saying is the first character we've got 26 possibilities, the next character we've got 25 possibilities, the third character we've got I should say 24 possibilities, my apologies, and so on. So what's happening is the number of possibilities is going to be 26 times 25 times 24 and so on, which you can see is a factorial. If we can, and we'll get, it will take us, it could take us an awful lot of tries to find the password. Equally, it says here, if we can reuse characters, so we can use the same character in any position, then we've got n to the 26, which is kind of, we're going to get an exponential type situation. Now, with the growth on that one. If we then take this expression here, which is log of n log n, and we look at a quick sort, and it uses recursion, we're going to see growth a lot along these lines. Now, this is an interesting one. So if you remember, on a quick sort, what we do is we've got our data set we want to sort. What we do is we pick an arbitrary pivot point. I'm going to pick this pivot point here. Now, where you set the pivot point is completely arbitrary, but for a given set of data, there will be a kind of a better pivot point. Often you would choose in the middle. In fact, most people would choose in the middle. What we then do is we then take we then go through our data. We'll start off over here. Let's imagine this has the value, I know, we'll put an H over here. What we do, and let's say our pivot is the letter O, the value H, we compare this to the O and we say, okay, that becomes before, so I'll put that in this half over here, and then the next value I'm going to have is going to be a W. I compare the W to the O and so that comes after the O, and that's going to go over here, and then I'm going to have the letter T, and that comes after the letter O, so it goes over here and so on. So we just basically read through the list, working out whether the item goes in before or after the pivot point, and we're going to generate one list over here, and then we're going to generate another list over here. And then for the next pass through the data, what we'll do is we'll look at this list here as a list on its own, and this list here on its own. We'll pick a pivot point, let's say this point here, and we then iterate through the list and compare each item in turn with a pivot point, and then put them in a left or right list. So you gradually work through and you generate smaller and smaller and smaller lists, which you're breaking up. What you can then do is take items and put them into, start to combine those together to make your result set. Now, if you look at this, the way that this quicksort works, if you're coding this recursively, the growth will be n log n, or n log to the base 2 of n. Again, notice you've got the binary, because this is using a kind of it's a divide and conquer algorithm. You're getting this kind of growth in accordance with a factor of 2. Now, the time complexity of this also depends on the number of items, because big lists takes a long time to search. We can see that, and then because we're dividing and conquering, we're going to get a logarithmic growth, as you say here. If we consider the best case scenario, which means we can split everything gets split evenly. If your data is skewed so it doesn't split evenly, then the time it takes longer to search to sort it. But if we start with 16 lists, they'll break down into 16, into 8, into 4, into 2, into 1, and so on. We get 4 calls. If we then double the number of items, we get 5 calls, and so on. And that means that we've got growth in accordance with logarithmic growth. We can see this because what's happening is every time you add you double the amount of data, you get one extra iteration. So each call performs n comparisons and then log n comparisons on the data you've got, which is why we get this n log n. I hope that makes sense. Now, if we plot all those out on a graph, you get a graph that looks a wee bit like this. So you can see this green line at the bottom here. This is constant time. Which an example there would be, this would be the kind of finding the length of an array. We've got logarithmic time here. So the example there was the binary search. You've got the straight line, which is the example we looked at there, was the linear search. And then at the top here, we've got these various different, we've got logarithmic growth, we've got n log n growth, and we've got the exponential growth, the polynomial time, which was the n squared. If you remember, the n squared was the nested loops kind of situation. So we can actually look at and make a kind of a best guess as to how long the algorithms are going to take to complete. Now, if we go on a little bit further, we can also look at this thing called space complexity. So time complexity is how long does the algorithm take to complete. Space complexity is how much data does it need, or how much storage space does it need, because if we need lots and lots of storage space, that may be a limiting factor in what we can do. So we look at, after we've looked at time, we might want to look at how much, say, stack space does the program need to use. Now, as it says here, most iterative algorithms have a constant growth rate. And we're talking here about space complexity rather than time complexity. So here we're talking about algorithms that just use iteration. They're just doing things like repeat loops, for loops, and so on. And generally speaking, if we're using a single data structure like an array, and what we're doing is we're just swapping things around. So if you think about like a lot of sort algorithms, if we've just got one array and we're sorting the data in place, there's no extra requirement on memory. So we've got constant growth in terms of space. And you really want to talk about growth in space in this situation. If you've got a recursion program, particularly if you're using things like stack, what happens is every time you make a kind of imagine, here's your function, and that then calls itself. What will happen is all the variables within here need to be added to the stack. So our stack starts off looking like this, and then the first call, it's going to add pop items onto the stack, or push items onto the stack. The next call, it's going to push items onto the stack, and so on. So amongst other things, it's putting in the return values. So our stack is growing up, and our space usage is growing with it. And the problem here is that well, the number of items that we put onto the stack is dependent on the number of times the recursive algorithm calls itself. So this can actually grow out of space quite quickly if you're not careful. The worst case scenario, of course, is you have this base condition with recursion, and if you remember, the base condition is the thing that causes the last call to return. So when you hit your base condition, the stack gets deallocated, and the top of the stack will kind of move down. The problem is if you don't hit your base condition early enough, you'll run the machine out of memory. Now, if we have like a quick sort, we can see logarithmic growth in terms of space. So as we said here, the number of calls halves each time, so we get the number of calls is log to the base 2 of n, or the amount, therefore we can say the space needed has an O of log to the base 2 of n, and that assumes, as we're saying, we're splitting everything evenly. If we've got a recursive binary search, we've got a space complexity, similar space complexity, but if we've got an iterative binary search, then we get constant space use. So you can see the problem here with iteration, we've got significant growth, but with iteration we've got zero growth in terms of space. So from the memory space kind of and storage requirements point of view, the iterative solution is much more efficient. With factorial here, what we can see is we get what you'll get is a growth rate that is proportional to the number of data items. So you get linear growth, and that's if you're looking at a recursive algorithm. With an iterative algorithm, you're going to get constant use space. And then if we've got you can look at this example if you want an illustration of that, which is if we're working out 6 factorial, we've got 6 calls. But if we did it iteratively, we haven't really got any calls. We've just got a single iteration, so constant use of space again. Now you can read more about this if you really want to on this website here. There's a hyperlink in the presentation, and if you want to But what I would recommend more usefully is probably go and have a look at this video here. This is by a YouTuber called who has a channel called CS Dojo, and he's a software engineer. Really good. He's got some really good stuff on his channel. So yeah, if you click this image in the slideshow, it will take you to that presentation or that video.